And first of all, I'd like to welcome you and thank you for spending about a little less than an hour with us here today to learn about how VivaBioCell builds mini bioreactors to actually grow new bone, which is a really fascinating application, and some of the components that they're creating for their mini bioreactor are 3D printed using the PROJET 3510 3D printer. So let me start by introducing today's speakers. I'm Tom Sharon. I am the VP of Product Marketing at 3D Systems. I have with me here today, actually not physically here, I'm in California, and Piero Fessore is in Italy. He is a designer with VivaBioCell and is going to talk about how they're actually using the PROJET 3510. And Derek Johnson, who is the Director of Printer Product Management at 3D Systems, will be joining us as well for the Q&A. So first, I'd like to introduce 3D Systems. If you're not familiar with who we are, we're a leading provider of 3D print-centric design to manufacturing solutions. What does that mean? So it means, of course, that we build 3D printers, a variety of 3D printers for a variety of different purposes. It also means that we provide materials for those printers. We provide on-demand parts so that you can order parts and we'll print them for you and ship them to you. It means that we provide software for 3D design as well as 3D scanning and inspection. And we also have a large healthcare group related to what VivaBioCell is doing inside of 3D Systems. We're pursuing a variety of different cutting-edge healthcare technologies using 3D printing or additive manufacturing. We really pride ourselves on leading through innovation and technology. And just a few of our achievements through history are that we invented 3D printing originally. Our founder, Chuck Hull, was the first to make a commercial 3D printer. And this was the stereolithography, or SLA, printer that was initially invented. The very first part was printed in 1983. And that system was commercialized in 1989, believe it or not. We also invented SLS, which is selective laser sintering, and put that on the market in 1992. We invented color jet printing, brought that to the market in 94. And multi-jet printing, which is the technology that drives the PROJET 3500 series that we're going to talk about today, we invented that in 1996. So I mentioned just a moment ago that 3D Systems really offers 3D printers for every need, from the living room and the classroom and the garage through to the desktop, the lab, and the factory. And we offer systems that cost less than $1,000. We offer systems that cost up to $1 million. And it's all about how much productivity do you need, what types of parts are you trying to print, in what materials, at what accuracies and resolutions. And we really offer the full gamut of different printing technologies. And we're going to talk today about one of those particular technologies. In fact, it's one of our more popular systems, the PROJET 3500 series. And when we look at how you can use 3D printing, we can broadly categorize it into 5 different areas. We have concept models, which are great for communication and idea sharing. And that's really all about printing things that look beautiful so that you can put them in front of a customer or you can put them in front of a decision maker to get a green light on an idea that you have. And then there's functional prototypes, and that's really about validating design ideas and engineering ideas. So this is where you're printing functional plastic parts or metal parts that you want to actually run tests on and validate your ideas. And then there's rapid tooling, which is all about getting to pre-production very quickly. And of course, we're seeing a very quick adoption of additive manufacturing for actual production parts. So this means making the parts that are not prototypes or not tooling, they're the actual end-use parts that are going to be installed in other systems or sold as products on their own. And the last category is what we call mass customization. And that's broadly a lot of healthcare applications and some other things where we're talking about making 100,000 or 1 million of something, but every single one of those is different and unique. And of course, a 3D printer, unlike traditional manufacturing methods, it doesn't have to create identical parts every time. Every single one can be different, and there's no cost difference to do that. So dental applications, almost all in-the-ear hearing aids now are 3D printed. That's like 97% of all hearing aids in the U.S. are 3D printed now, and a variety of other medical applications. Now with that, I'm going to hand it over to Piero Fessore from VivaBioCell, and I'm going to let him introduce his company and talk to you about how they're using printing.
Okay, thank you, Tom. My name is Piero Fessore, and I'm a designer and 3D modeler at VivaBioCell. And thanks a lot for having us, because we are really glad for this opportunity to share with you all our story on how actually 3D printing with 3D systems really enabled us to achieve essential goals in our work. And before jumping into the presentation, please allow me to quickly introduce VivaBioCell. And we are a technology-oriented medtech company based in Udine, Italy. And we work in the field of regenerative medicine, developing devices for stem cells-based therapies that restore, repair, maintain, or improve the function of human tissues. And we do it ensuring healthcare quality through high automation and safety, standardization, and lower costs with respect to traditional medicine. And actually, talking about devices, we are currently developing an automated continuous cell culture device, which actually is a bioreactor. And basically, a small sample of patient stem cells is amplified through a microfluidic system and then attached onto a small biocompatible three-dimensional structure, which is called the scaffold. And the scaffold is then implanted into the patient as a bone substitute. And we will cover all the details in a minute. And we are a multidisciplinary but small team, so these big design challenges need a creative approach, and let me say, not just a traditional one. So here is our scaffold and the core component of our system, where, as we said, cells attach and grow. And as you can see, it is really tiny. We are talking about 1 centimeter cube, or 0.4 inches, but has a quite complex and precise geometry in order to ensure the exact laminar flow of nutrients during the culture. And actually, here is where the design challenge starts, because we need, let me say, a container for the scaffold in order to place it along the microfluidic system and let the nutrient fluid flow uniformly. So that all the cells are optimally fitted. And being the scaffold so precise, its container needs, of course, an equally precise shape all around it. And we call it the cell culture chamber. The cell culture chamber needs all the following features, and it needs to be transparent so we can observe the scaffold inside, like, let me say an example, being sure there are no bubbles disturbing the flow. And its materials need to be biocompatible, non-toxic for cells, because you know there are stem cells inside. And it needs to have an extremely precise geometry, as we saw earlier. And because the cell culture chamber is a disposable part of the bioreactor system, I mean to avoid cross-contamination between cells coming from different patients, it is crucial, it is not expensive. Okay, so enough design. This is an actual prototype that we made a few months ago, produced by traditional manufacturing. And as you can see, the scaffold is inside, along with other small components containing fluid channels, small pipes for inlet and outlet, fluidic connections, gaskets, and so on. So let me disassemble it for you. And actually, yeah, you can see it's a lot of parts and a lot of materials too. Actually, it's 14 different parts and 6 different materials. And as we said, this cell culture chamber prototype was produced by traditional manufacturer, and it was really expensive and not even close to the degree of detail that we needed. Kind of dead end, because it simply didn't work. And we defined every characteristic and considered many traditional manufacturing processes, but none of them had the answer that we were looking for. So we sat down in the lab and said, maybe we are doing it the wrong way, and because we need a technology which is really suitable for the manufacturing of the cell culture chamber and not the other way around. So we thought, is there another way? And the answer is that exactly in that moment we thought about 3D printing for the first time. And we just started over, and we sat in front of the computer and started modeling, following what was our ideal idea of what we thought our cell culture chamber should look like. And of course, when you have a virtual model, you can run simulations on it, like fluid dynamics simulation in our case. And we instantly understood how many optimization we could do to increase the cell culture chamber performances. Like as you can see here, for example, how really small but really efficient shape is, and we are talking about 0.3 millimeters and 0.08 inches, quite impossible to achieve, I mean inexpensively, using traditional manufacturing. So we had our virtual model and started looking for a 3D printing service some months ago. But surprisingly, we've been told for weeks from different suppliers, and sorry, we can't meet all of your specifications. And we were really close to abandon the idea of 3D printing when we finally found Prototech Celtech, which is a 3D Systems Italian service provider. And it proved to be a very professional team able to support us to meet every single specification, from transparency to biocompatibility, from precision to low costs. And so here they are, finally, our first 3D printed prototypes right on the table of our lab. And because of the low costs and ease of modeling, we were able to print a bunch of slightly different versions so we could precisely test different aspects of our design, like transparency, leak-proof closing, and ergonomics also. And at the end of testing, here it is, our ultimate prototype, and actually the production part. And if you do remember the traditional manufactured cell culture chamber from where we have started, we'd like to look at the differences. And as we did earlier, let me disassemble it for you. And as you can see, we are talking about 2 parts instead of 14, and one and only material instead of 6. And you know what? We are also talking about 7% the price. And I mean, it's a kind of Disneyland for designers, and really a dream for our managers too. And the awesome part, this is not a prototype for future traditional manufacturing, but it is the actual fully functional component ready to be plugged in and used into our bioreactor. And it works because we can really grow stem cells inside it just out of the printer. So we really think this is awesome. And maybe we forgot to mention that this is the first time ever VivaBioCell uses 3D printing. And let me say the design process felt so intuitive and natural. I'm talking here from my point of view as a 3D CAD modeler and designer. And it's really incredible how many ideas came up when you grab a printed object in your hands while developing a product. And this really allows you to refine every aspect of it. And let me say, you feel like you can really achieve not just a good design, but actually the right design. So that was our story. And again, thank you so much for having us.
Yeah, very interesting indeed, and we're very happy to see the success that you've had by using 3D printing. What I'd like to do is now talk about the specific 3D printer that was used to print these reactor chambers for VivaBioCell. And that is the PROJET 3500 series of plastic printers. And this particular line of printers that we offer is all about printing functional plastic parts in high definition very easily. So that's the focus of these 3D printers, and it's a great fit for what VivaBioCell needed. So you can print concept models as well as functional prototypes that are extremely accurate, high resolution, and tough. And these printers use multi-jet printing technology, which we call MJP for short. And the way they work is they use hundreds of individual jets to print plastic parts using materials that range from ABS-like hard plastics to polycarbonate-like optically clear parts in a variety of different colors, and we offer biocompatibility and various other features of the different materials that can be printed using the PROJET 3500 series. And we offer a variety of different configurations of this printer to meet specific requirements with different resolution levels, build volumes, and different materials that they can run. So why choose PROJET 3500 for plastic parts? As I mentioned earlier, you get really superior quality functional plastic parts, and they print quickly. The parts are very high resolution with sharp edges, crisp details, and smooth surfaces. So you can see some of the examples here. You know, these blue hexagon models that you see at the bottom right are very small. They're not much bigger than your finger, and yet we're able to print the holes on those very, very accurately. The printer is intuitive and easy to use. It's office friendly, so it can sit in your office. and you can test more ideas faster and very economically using this printer. So I just want to show you more images of the parts, because when you hold a part from a PROJET 3500 in your hand and you look at it, you can see immediately the quality of the part, and you can feel the toughness of the material. And that's something that's, of course, over this webinar, you can't feel the parts, but looking at the images, you can see the sharpness and the detail that's available. And the upper left image here shows a little bit of the toughness that's possible with this system, because that's a hydroformed sheet metal part over a mold that was printed in a PROJET 3500 printer. So this is able to take the very high pressures of hydroforming and have sheet metal fit around it. I mentioned earlier the microfine detail resolution. This is really key. When you're looking for really, really sharp, accurate, beautiful parts, the PROJET 3500 series does very well with that. You need a loupe, actually, to see some of the levels of detail that this printer can print. This little Buddha statue is only a few centimeters tall, to give you an idea of scale. And very important for when you're trying to assemble parts together, if you want to print something and put it in assembly, is that you have consistently sharp edges and corners. So you can see some of these electrical connectors, the very fine detail and sharp edges that we're able to keep. Not all 3D printers and some of the competitive systems to the PROJET 3500 series cannot produce this level of sharpness and detail on their parts. It's one of the things that the 3500 series from 3D Systems excels at. And the system, the parts that come off of the system not only look good, they're very, very accurate and have very good precision. And you know, what we recommend to do as you look at different 3D printers and consider them, get a part printed and actually compare it, measure it. That's how you'll know for sure whether the system that you're looking at is accurate or not. And just as important as the printer itself are the materials that the printer can run. And the VivaJet line of materials that the PROJET 3500 series can run are engineered materials that match the printer perfectly and do very, very well with it. So we have a variety of different materials, as you can see here. The third one over from the right, the VivaJet M3 Crystal, this is the material that VivaBioCell used, and it met their requirements very well. It's translucent, it's a tough material, it's ABS-like in its material properties, and it's very importantly, it's Class 6 certified for medical applications. So it's a biocompatible material as it comes out of the printer. And then we have a variety of other materials as well that you can see here. The PROJET 3500 series is all about maximum throughput, minimum effort, and minimum time and cost. And so the printer can be operated from your iPad or your Android phone or your iPhone. You can manage print jobs remotely. You can pause and start builds. You can check the status of things. You don't need to go over to the printer. The printer just sits on a corporate network, and you can send jobs to it as needed. Very easy connectivity, and it has automated processing from file to ready-to-use part. It's economical to own. We include a 5-year warranty on the printhead in this system, and that's important because some 3D printers go through printheads very frequently, and it's a hidden expense that you need to take into consideration when you're looking at different printers. The PROJET 3500 can print more parts faster. One of the really key things, and you can see this in the image in the upper right, is that because of the way that the printer prints and the support material that we use, which is a wax material, we are able to vertically stack and nest parts within the build volume. And that's a unique capability among jetting systems of 3D printers, that you can print one part on top of another, and the system will just print wax support underneath the part above to hold it up over the lower part. So that means you can take advantage of more of the build volume. If you take advantage of the total vertical build volume to build more parts in a single print run. So these are very productive printers. And I mentioned early on that there are several different models of the 3500 series plastic printers. There's the PROJET 3510 SD, which is focused on affordability and offers 32 micron layers in its HD mode. And you can see the build size there and then the build speed as well. And then you can move up to the 3510 HD, which is a higher definition system. The 3510 HD Plus adds more flexibility. It can go to a higher resolution and can build in a larger volume for the HD print mode. And then the 3500 HD Max has maximum throughput, and you can see all of the different print modes that we offer, and that's when you need to balance speed with precision and accuracy that you can print. And then the build volume. There's no reduction in build volume no matter what mode you're printing in on a 3500 HD Max. And I don't have a slide on this, but I also want to mention that the 3500 series, we make systems that not only print in plastic, but also print in a wax material. So I mentioned a moment ago that the support material on a 3500 is wax. And that has the benefit that when you're done printing the part, the post-processing is very easy. You can simply melt the wax away by putting the parts in an oven, and the support wax has a low melting point, so it will melt away and leave the plastic parts. We also make a series of 3500 printers that can print in wax as the part material. And so it's a higher temperature wax, so that the lower temperature support wax will actually melt away, and you'll be left with a wax pattern, and that is for castings. So those wax patterns that you can print, as opposed to the plastic parts that you can print, can be used in regular foundry processes for lost wax, sacrificial pattern casting applications. So you can get metal parts through an additional step using the PROJET 3500 series. All right, so with that, I'm going to welcome my colleague Derek Johnson from 3D Systems. Derek is a technical expert on the PROJET 3500 series as Director of Product Management. So he'll be able to answer some questions that come up about the printer itself. And of course, Piero from VivaBioCell will be able to answer questions specific to how they view the 3D printer. So one question is, was this part printed on a PROJET 3510 MP? Derek, do you want to answer that one?
Yeah, so the PROJET MP 3510 is a extremely niche printer that's used primarily in the dental field. The material that they use for their prototyping and eventual production testing is not compatible with the MP, so their work was not done on an MP. The materials that run in the MP are very specific to the dental field, and so the materials that they were able to use are compatible with a PROJET HD. And so we have different models of printer, and more than likely they were printing on a PROJET HD printer. And I think Tom mentioned it earlier in the webinar that the material is VivaJet M3 Crystal.
And that answers the next question, actually, which was, what is the printed material? Here's a question that I think Piero can answer. Is the scaffolding itself 3D printed as well, or just the chamber? If not, how is the scaffold made?
Yeah. the chamber, it's actually 3D printed, and the scaffold, it's not, because right now it's produced by injection molding, and that's because of the kind of problems of the geometry. But first of all, the material itself, because the chamber just have to be biocompatible because of the stem cells are inside, but the scaffold itself, it will be implanted. So it's part of our future developing, just trying to find a way to actually print the scaffold directly. And just to answer to another question about the scaffold, as we can produce the scaffold by 3D printing, we can also producing it on the based on the shape, the actual shape of the patient's knee. And so this is part of the future developing of this device, which has this bioreactor has really many components, and we're just the chamber was just the first one we've designed, thinking the 3D printing way. But it actually opened us just a new world. So we'd like to go deeply into it. And actually, the scaffold, 3D printing scaffold, is in the future of the developing plan. And just one thing. As long as my colleagues, which are the biologists, I'm just a designer and modeler, so for the biological stuff, I think you can mail us all your questions, so in the next few days we can reply to everyone.
Yes, and if that's a good point, Piero. If any of your questions can't be answered today, either because of time or if they're specific to the biology or something like that one of us on the webinar can't answer, we will follow up with you in email because the system records your questions, and we'll be following up with you if we aren't able to answer them right now. Well, we have another good question here. Can multiple materials be printed at the same time? Derek, do you want to take that one?
Yes, so right now, and I think there was another question further down, someone asked if you could print over metal. Today we don't have a 3D printer that allows you to print plastic over metal. Typically, but one of the benefits of the material, specifically of the material that they use in this particular application, is that you can drill it, you can tap it, so you can add additional components to a metal, to a plastic piece in an additional process. So today, it's not possible to have a metal material and a plastic material blended inside the printer. Now, we do have another 3D printer, the PROJET 5500X, which allows you to blend a rigid plastic and a flexible plastic inside the printer to create composite materials. So, for example, if you had a, in their example, if you had his culture and he decided he wanted a rubber gasket, he'd be able to design the rubber gasket in, and it would be printed as a plastic chamber with rubber gaskets, placed where they designed it. So we do have another printer that allows you to do multi-material printing, but it's still two plastic components, one having rigid mechanical properties and the other having elastomeric mechanical properties.
And there's another question here, which is, can you provide material for building a business case for 3D printing? Target markets being textural models, prosthetic device manufacturing, DLA parts for DoD. And there's actually a very good white paper created by Deloitte Consulting it doesn't exactly make a business case for 3D printing, but it does talk about the very high-level sort of business considerations of 3D printing and some of the advantages that are out there. And to the gentleman who asked that question, we'll send you an email with that link specifically. But if you go on the 3dsystems.com website and search for Deloitte, you will find a link to that particular white paper as well. And that's a really good tool. It's not a marketing piece. It's made by a third-party, business consulting firm that talks about the considerations and some of the things from a business perspective of adopting 3D printing. There's a question here about, I have heard that the post-processing is very time-consuming for multi-jet printing, the MJP technology. Derek, do you want to answer that?
Yeah, so I answered it privately, but I told him I was going to answer it publicly so that I could share the process with everyone. And Tom mentioned it earlier. One unique attribute of our materials is the support material, and it's a wax. It's just a plain paraffin wax that is printed to fill in all of the voids, overhangs, and to completely support the part during printing. As you know, the easiest way to get rid of wax is to heat it up. So we have a finisher oven that allows you to put your parts in the oven and it melts out the wax. As long as the wax has some way to flow out of the part, you can have an extremely complex, detailed part. And as long as there's an exit path for that wax, the wax melts right off. That's a big benefit, particularly in applications similar to what we talked about today, where you have very tiny channels, very fine features that you would not want to damage using, any kind of high-pressure washing or corrosive soaking solution. The heat lets the wax melt out. There's a secondary step that allows you to remove any residual wax that might still be clinging to the part, and then it's a matter of washing the part off and drying it. So the process is very hands-free. It's not labor-intensive, and it allows you to do batch post-processing, which is important because if you're cleaning 100 parts, you don't want to have to hand-hold each one of those parts and do something with them. That takes a lot of time, a lot of labor that can cause your cost to add up over time as you look at your total print-to-part process. So that's the process. Of course, every geometry is different, so every geometry requires a slightly different amount of time in the finisher oven to make sure that all those support wax is removed. So what we do, what our resellers are trained to do is work with our customers, and if they have any difficulty in post-processing, we have application specialists that are available to help out and provide, kind of advanced training or troubleshooting if there are any difficulties in post-processing.
Here's a question that I think Piero can answer. Derek could too, but we'll let Piero take a shot at this one. What is the minimum sharp edge radius that can be achieved?
Yeah, I'm not going to talk about the actual one, but we have a few of sharp edges inside our chamber, and because we are in a lab, we also have access to the microscope, so we could really look really close to the sharp edges, and as far as we could see from the microscope, I think they are just sharp, as it said, and so I don't know technically the printer, which is the parameter, but actually also looking at from the microscope, they are just 90 degrees sharp edges.
Yeah, just to add on to that, I don't have a specific spec on that particular thing. I think within the description it talked about feature size, but we don't have an exact spec on sharp angles. But honestly, the best way to answer that question is to actually look at a part. And I think Tom mentioned that when we give specifications on minimum wall thickness and so forth, you know, it's highly geometry specific, and a lot of times the geometries that we see printed far exceed what we say is our limitation. So we don't like to put the limitations as an absolute. It's definitely just the guide. But for that particular specification, I don't know. But we know that when we print round circles and edges, they are extremely sharp, which can be verified, like he mentioned, you know, through viewing parts microscopically. We're able to do extremely fine features and high-level detail on edges and so forth.
Derek, do you want to explain technically why it is that we can hold such sharp edges on the SAP systems?
So with multi-jet printing, and this is unique in the industry in terms of our printing process, it's important to remember that inkjet printing processes are not all created equal. With our printing process, our material is what we call phase change, which means that at elevated temperatures, it's liquid, but at lower temperatures, it solidifies. So we're printing droplets of plastic and wax material out of our print head. When those droplets hit the build platform, they freeze in place. This is very different from, for example, a liquid plastic that is liquid at room temperature. You can think of a pancake batter, and when you pour pancake batter, it likes to run. When our droplets are jetted out, when they hit the platform, they freeze because they started the cooling process. The phase change nature of the materials allows them to freeze on contact. So when we jet a droplet, we know exactly where we're going to put it, and we know that it's going to stay there. So if I'm jetting one drop on top of another drop on top of another drop, I don't have any runover or runoff, and that allows me to create very sharp corners, very well-defined edges, and that's what helps to define the angles, the sharp angles that were mentioned by the question.
Here's a quick one to answer. Do you have any metal printers?
We do have metal printers. We have a family of metal printers, the ProX 100, 200, and 300. Those are direct metal printers that offer a variety of different metals for printing, some of which include titanium, stainless steel, aluminum, various tool steels. We have more information on our direct metal printing systems on our corporate website. So you can visit 3dsystems.com to find more information about our metal printers.
Here's a question. Is there a biocompatible material for the PROJET 460 Plus?
I'm not quite sure about that. My thinking is that there is not. There are not different material types. We have a core material, which is the powder that is actually used to create the part, and then a binder that is used to create the color. I'm not sure if either one of those are biocompatible. And we have to remember when we talk about biocompatibility, there are a lot of different elements to that. It's, you know, the most extreme would be implantable, something that's permanent to be implantable in the body. And for the most part, most 3D printed materials are not implantable. If you're looking for an implantable solution, a lot of people go if you're looking for a 3D printed solution, a lot of people are then going to the metal printing, where you can print in titanium. You know, a few steps back from implantability are exactly what they are doing, which is stem cell testing. And the most important consideration is that the plastic does not have adverse effects on the cells and resulting tissue that's being grown in various medical applications. Or if you are designing, for example, pill cases, that there's no leaking of anything that would be toxic or harmful in the processing or testing of those of that part in that medical application. And so the VivaJet M3 crystal, and we have another material on our SLA technology that are certifiable for short-term contact with human skin, as well as extended contact with cells, as we see in this particular application.
Okay, here's a question for Piero. how much, if any, post-processing of the threads was required on the device that you printed to allow for sealing of the device?
Yeah, I'd like to answer to Ken and Chad regarding the sealing aspect. And this was quite a fun part of the design and manufacturing because, as we said, we passed through a few different versions of the chamber. And if you do remember, the first one, which was produced by traditional manufacturing, has two gaskets, so for the liquid not to spill out. And so the first time that we made the first prototype for 3D printing, we just said, okay, we don't know how are the tolerances from 3D printing, so we just decided to keep the rubber gasket into the first prototype, and it quite worked. But we also have two kind of threads in our design, and the first one is the one that keeps the top with the joint with the container of the scaffold, and that was the printing is so precise that actually the first one had one drop of liquid outside because of the tolerances that we thought that the printer could reach. And actually the printer is so precise that we actually had to reduce the spaces from manufacturers in order to have the actual sealing. And the other thread we have threading, it's for inlet and outlet of the chamber, and because before we had two standard components to join the chamber into the microfluidic system, and we thought that's the first time we thought that we could maybe reproduce the threading into the model itself, and that was the first part, and it actually worked perfectly. And then we said, okay, let's remove the gasket and try to have just two parts without the gaskets, and the printer is so precise we could actually achieve it without any other components. So this was maybe one of the most interesting part of that design.
Okay, thank you, Piero. So we have time for just a couple more questions. One here is asking the specs that we note on the slide in terms of the layer thickness and that sort of thing. We note that it's, for example, 32 microns, and that is in metric. There was a question, are we stating that in inches or in metric? That is metric. So, in other words, 0.032 millimeters is the layer thickness in that example. Another question here from Antonia. Hello, Antonia. Good to have you here. Is how long does it take to change from one material to another in the PROJET 3500? And Derek, do you want to answer that?
Yes. So we have a change-out wizard that allows the user to press a couple of buttons and go through the change-out procedures. It's very simple. Takes a couple of hours to do a complete changeover. So if somebody starts, early in the morning, they're loading. They take their old material out, put the new material in, and go through the change-out wizard. That process basically involves going to a screen, pressing a couple of buttons, and then the machine does everything else. It even prints out a kind of a test print afterwards to verify that you have changed to that new material. We do have darker materials. We have VivaJet M3 Black, which is a polypropylene-like material. It's deep, dark, opaque black. So going from a black material back to like crystal, for example, does require a little bit more in terms of the process. So that process is a little bit longer, more like 4 to 6 hours. That's more of a drastic change since you're going from basically a black to a transparent clear. But generally going from our clear material to, for example, our opaque white material is a couple of hour process.
Great. Well, I think so. We're at the top of the hour now. I think it's a good time to wrap up. So again, I'd very much like to thank Piero and his colleagues at VivaBioCell for spending some time here with us today. Again, we're very happy that you've been able to see the success that you have using 3D printing, and we look forward to continuing to work with you. And Derek, I'd like to thank you as well for joining us here and answering questions.
No problem.
With that,
thank you.
Thank you so much. Have a great day, everyone. Bye-bye.
Thank you.
Thanks.